Welcome back, everyone, to this week's Algebraic Graph Theory seminar. This week we have Peter Dukes talking about fractional Sudoku.
Thank you very much, Sabrina. I appreciate the invitation very much. And also thanks to Maria and others involved here. And thanks to everybody for showing up. Okay, so I want to start by saying I don't know how to play Sudoku. I'm not very good at these sort of puzzles, but I want to tell you a little bit about something a little easier, so fractional Sudoku. And this is joint work with my student, Kate, who is here as well. And actually, Kate is in Montreal and just presented this, I think yesterday or recently anyway, at the CMS meeting with a poster and a talk. So let's get started with just an overview of what we'll be doing. So first, just an introduction to the notion of partial Latin squares, which is maybe the precursor to Sudoku from at least a mathematical point of view. We'll tell you about sparsity conditions that we need in order to guarantee that we can always complete such things, that is to solve the puzzle. Okay, so we're going to basically proceed in a very naive way. We're just going to set up a linear system of equations. And I guess that's where this starts to turn into something algebraic for this seminar. We will set up a matrix that lives in a coherent configuration and be able to use that to compute its inverse and solve to get our solution. So along the way, we'll tour the associated eigenvalues and eigenvectors that are necessary to get this generalized inverse we need. And then there's a little bit of perturbation stuff, which is maybe also of interest for the sort of algebraic graph theory world. It's something that could possibly be useful in other regimes, I guess. Okay, and then a few remarks at the end. So with that, I guess we'll start with the intro here. This is probably a reminder for everybody. And, if you've played Sudoku, I mean, who hasn't? This is probably very, very natural. But just to pin down some definitions and notation, a Latin square of order n is an n by n array. The entries are filled with one of n symbols, let's say the first n positive integers. And the condition we need for a Latin square is that each symbol occurs exactly once in every row and in every column. Okay, so when you don't maybe have everything filled, but you haven't violated two or more in any row or column, then you have what's called a partial Latin square. And as you might expect, a completion of a partial Latin square is just a Latin square that contains the partial Latin square in the sense that they agree on their filled entries. Okay, so we want to, you might imagine a game much like Sudoku, you have a few entries filled into a partial Latin square of order n, and then you're asked, can you complete it to a Latin square of the same order? And so here's an example of that kind of game in action here. We have a partial Latin square of order 5 on the left, and then a completion of it over on the right. Can everybody hear me and see everything okay? Is everything looking good? All right, awesome, thanks. Okay, so we can't use any row or column or symbol very often if we want to have a completion. Now, here's a really annoying so some jerk gave us a partial Latin square over on the left here where the whole first row is filled except for the last entry. And then they put the symbol we need not in that row. So that's no good. We can't complete that, of course. Basically, the transpose of this is shown in the middle. And then kind of another variant of this where I guess the roles of symbol and symbol's been sort of switched into a role like a row or column where the first symbol has been used way too often, except we're not allowed to put it where we need. So in these cases, this sort of shows that if we want to guarantee a completion, we better not use any row or column or symbol very often. But I mean, this is quite extreme. This is letting the puzzle creator use almost the entire first row, say. But we can still run into problems even if we have about a quarter of the thing filled in this way. So let me try to explain. Well, you probably all can picture, let's just start with this. If I give you if I give you a 2x2 partial Latin square where I put a 1 and a 2 along the main diagonal, you're not going to be able to complete that because a similar reason as we just saw before. Actually, it's actually kind of all of those problems from the previous slide happen in the 2x2 case if you just put 1 and 2 on the diagonal. Well, this is something kind of analogous to that here. What we're going to do is we're going to populate the top left quadrant with about a half filled. It doesn't really matter how you do it. Just make it about half filled with the low symbols. That's the sort of first half of the symbol set. And then put the same kind of thing, about half filled high symbols on the lower right. Now, the trouble with this is that it will force us, filling with a little bit more than half low on the left will force us in the top right to put at least half or maybe slightly greater than half high symbols. But the problem is the high symbols below it force at least or maybe slightly greater than half low symbols to be here as well. And there's just not enough room to put all those symbols. So you could think of a 4x4 example. I probably should have put that down, but the example gets more sparse, I guess, as n grows. So yeah, maybe you still don't want to use any row, column, or symbol that often where maybe up to a quarter. Notice that, say, the first row of this array here could be only slightly more than a quarter filled with the low symbols. And likewise, like a column over on the right is only about just slightly more than a quarter filled. Okay, so that's maybe an important barrier to discuss to set the stage or set the boundaries, so to speak, of what we could expect to complete. And I haven't yet defined what I mean by fractional completion, but really this barrier, if you like, it's truly a space barrier. It's like a geometric constraint where it doesn't even matter if you're allowed to cut up your symbols fractionally. There's just not enough room to put what you need in the rest of the unfilled entries. Okay, so let's move on to defining something that might link nicely with this barrier. So we're going to say that a partial Latin square is epsilon dense if no row, column, or symbol is used more than epsilon n times. Okay, now you might reasonably expect that epsilon dense Latin squares can be completed if epsilon is small enough, maybe underneath that barrier that we just saw. So there is a theorem, or it's actually a progression of results, I suppose, that work toward that conjecture, if you like. It says that for sufficiently large n, every epsilon dense partial Latin square of order n has a completion. Back in the 80s, it was shown that for a sublinear but still fairly interesting proportion of the cells filled in, maybe it was something like order of root n occurrences of a symbol in each row and column, and each symbol occurring about root n times, or something like that, some partial results involving special values of n. But the first time that a positive epsilon was obtained for a theorem of this type was in 1991 in the thesis of Gustafson. And epsilon was pretty small, 10 to the minus 7. That was part of a larger work of Gustafson's on completing more general structures and triangle decompositions as well. So then a little more recently, in 2013, Bartlett showed that you can complete epsilon dense partial Latin squares for epsilon about 10 to the minus 4. And then a little more recently with my master's student, Flora Bowditch, we were able to increase this epsilon to about 4%. Okay, so the conjecture coming from the slide before, I guess, would be that you may be able to do this for epsilon as big as 0.25. So we're still a long way from that. Okay, but maybe there's some new ideas that can help with raising this epsilon a little bit to get a guarantee for completion of partial Latin squares. Now, I should clarify something important here. The last result for 0.04, Flora and I only really did a small step in this direction, and most of the heavy lifting was carried by the work of some others. Barber, Kuhn, Lowe, Ostis, and Taylor. They had a result that said, if you can solve the fractional problem for a given value of epsilon, then that will work for possibly larger instances in the exact sense that you can actually get a completion of your partial Latin square. I'm going to tell you about what I mean by fractional in a sec, but you may have a sense of what I mean. But we'll be basically proceeding along the same sort of route as that for Sudoku. So I'll tell you a bit about Sudoku, I guess, although you probably already know it, but we're going to be looking at general size. So we're going to have a pair of integers, at least two, h and w, and n is h times w. And just like in the puzzles you see in the magazines and online, so you've got a rectangular grid of boxes. So it's each box is h by w, sort of a height by width, and there's a w by h pattern of these that fits into an n by n array. Just like with a partial Latin square, a partial Sudoku is just a partial Latin square where you don't use a symbol too often in a box. Oh, I should say, for anybody who doesn't know, the important part about the Sudoku is that in addition to the Latin square conditions, we aren't allowed to have a symbol occurring in a box more than once. And that means that the box, since the box has n cells in it, the box has every integer from 1 to n when we've completed it. Okay, so a partial Sudoku just has the equality replaced by at most, just like in the case of Latin squares. They need not be completable, as we'll see in a sec, but when you can find a Sudoku containing partial Sudoku Latin square inside of it, then that partial Sudoku has this completion. So let's see some barriers for this problem. So if the jerk gave you this puzzle here, of course you couldn't complete it because you need to put the 9 in the box, in the first box there, and you can't because it's already somewhere else in the third row. So I guess what this is meant to show, this is very naive, obviously, but it's meant to show that you aren't going to be able to get away with the same notion of density as we had before, because if n is really big here, and you have about root n by root n boxes, we've only used each symbol once, and we've only used each row and each column root n times, and that's and that's of course sublinear, right? So if we want to be able to complete anything that's say 1% filled or something, in the sense of each row, column, and symbol used at most root n, at most 1% or something, we won't be able to do it. So we need some kind of a condition on boxes, I guess. That's important here. But okay, fine. Let's just say we use each row, column, symbol, and box at most epsilon n times. Here, the box has been used almost fully, right? So that may help us in our density assumption. Okay, but actually we need more. Consider this partial Sudoku. So basically some jerk has put about 2 root n occurrences of 1 and 2 in such a way that I can't fill the top left entry with anything. I need to put a 1 there, and I need to put a 2 there, right? So the problem here is that we've basically overloaded the row bundle at the top and the column bundle also over on the left, right? So so if you allow me to define a row bundle and a column bundle in this sort of natural way, we want a stronger sparsity assumption that not only do we want each row, column, and box to have at most epsilon n filled cells, but we need the same for symbols, but we actually moreover need that we can't have a symbol occurring very often in a bundle of rows or a bundle of columns. Well, I should say maybe a variation on this definition could still allow for completion. It would be interesting to explore further barriers, and perhaps some people in the puzzle community or others know about something that might be a little more challenging than this. But let's just say, to make our lives easier, we're going to be targeting the case of sparse partial Sudoku, in the sense that we don't want to use any row, column, or box more than epsilon n times. Epsilon we're going to think is some small number. We're going to actually get a value for it that sort of works in a certain weak sense. And we're going to have this bundle condition. Okay. So symbols don't occur very often in bundles, and very often is relative to the size of that bundle. Okay. Now, the question that is natural here is, can epsilon dense Sudoku always be completed for some epsilon? Pick any even very, very small epsilon. Could we get this to work? Well, we don't have an answer to this, but we do have an answer in the fractional relaxation of the problem. Okay, so I'll tell you about that soon here. The linear system of equations that's associated with Sudoku is it's pretty simple. We sort of have some Latin square type conditions here first. So okay, just to this is a lot of text, so to help out here, we're going to have let's say our rows are denoted R sub I, our columns are C sub J, symbols are S sub K, and boxes are B sub L. Maybe you can see my mouse, it might help to point to some things. Okay, now Xijk, we can let that represent the number or fraction, if you like, of symbols Sk placed in cell Ij. That's row I, column J. Now, Sudoku constraints correspond to linear equations on these Xijks. For instance, every cell having exactly one symbol. You might not think that's necessary, but in the fractional relaxation, it will turn out that these Xijks will be allowed to take on non-zero 1 values. But anyway, we want 1 for each Ij pair. So each row column pair, I need 1 symbol. For each Ik pair, that's a row, choice of a row and a symbol. I would like that symbol to occur somewhere in that row. So I need the sum of the variables Xijk over J, that is the sum over column indices, to equal 1. And likewise, I need every column to have every symbol once. So if I fix a column, fix a symbol, and I sum over the rows, then I need to have 1 there. Now, also, we can have a box condition that's easy enough to write down. So we just, it might be a little funny compared to these other things, but we just sum over the cells Ij that are contained in box L. And I would like the total number of occurrences of a given symbol K to be equal to 1. That is, I want symbol K to occur exactly once in box L. All right, so now we can set this up as a 4n squared by n cubed linear system. So just to get the dimensions right, there are 4n squared equations here. You see those, right? Basically, they're quantified over 4 types of pairs. We have row column, row symbol, column symbol, and symbol box. Okay, and then there are n cubed variables, Xijk. Notice that if I tell you where what row and column the symbol's in, then the box is defined as some like um, just a function of those, right? So, all right, let's let W be the coefficient matrix, which is just zeros and ones, right? So W times a vector X that holds the xijk's, we'd like it to equal the all ones vector of dimension 4n squared. That means we've solved each equation by this choice of xijk variables. Now, there is a naive solution, but you wouldn't get any credit for solving an actual Sudoku this way. You would just say, okay, I'm going to let I'm basically going to take every symbol equally often everywhere. Okay, and equally often would be 1 over n times. Okay, so now it's easy to see that all those equations are satisfied, right? Because there are basically going to be n ways to extend one of these pairs to a valid placement of symbol. And if every value is 1 over n, then we win. Now, this turns out to be, it's not very interesting from a puzzle point of view, as I say, but it is going to be really useful in our analysis of this work that we did. Now, okay, if some entries have been pre-filled, you could use a similar linear system. You just have to maybe adjust the equations of variables a little bit. Maybe don't allow use of the variables that correspond to already placed things, right? Or even things that could conflict with already placed things. For example, if in the 2, 3 position we have the symbol 7, then x237 should not be used. And moreover, we don't want to have x23 anything because 2, 3 symbol has already, the 2, 3 entries already been filled. So you get fewer variables. You do get fewer equations as well. Maybe you could try to solve that to solve your Sudoku. Okay, if you do it with 0, 1 value variables, then you actually get a completion. But this is the maybe key point about what a fractional Sudoku is. It's taken me long enough to explain to you. But finally, if we have a solution to this linear system of equations that is basically non-negative real valued, it won't be bigger than 1 for any variable in that case, I guess. So if the values take on this range, the closed interval from 0 to 1, then we'll call that a fractional completion. So it's just a weakening of what you would expect. Okay, so you can maybe think of Sudoku with this model as, or a certain way to think of it that maybe helps is a graph decomposition model. So we've got a 4-partite balanced graph here. So it's got 4n vertices. We've got rows, we got columns, we got symbols, we got boxes, n of each. And basically we've got this, maybe think of a big graph where all those equations that weren't satisfied a couple slides ago have been kind of represented with an edge. So at the outset, if you have a totally empty Sudoku, you've maybe got you need to kind of use up all the edges between rows and columns, between rows and symbols, and between columns and symbols. And you also need to use up every symbol in every box. So we have sort of complete, if you like, we have a blow up of a K3 plus an extra edge here. Blow up by n in each partite set. Okay, so we want to decompose this into these gadgets or tiles, which are a choice of a row, column, symbol, and box, where the box has to make sense for the row and column. So it has to be that the box, say B sub L, that's chosen for this tile should be the box that where cell ij would be. So we've got certain valid tiles, and we'd like a tile decomposition of this 4-partite graph. Now, if we have an honest to goodness tile decomposition, again, we have completed or solved, we have Sudoku. If we just have a fractional decomposition into tiles, then we have a fractional solution to our Sudoku. Of course, if things have been partially filled in, we just erase the corresponding edges. For example, if, as I said before, row 2, column 3 has already been filled in, then we have no edge there, and we want to just use tiles that avoid that. All right, so here's a look at the the relevant matrix W that we had before. So it was 4n squared by n cubed. You can now think of it this way: there are 4n squared edges, and there are n cubed tiles. That's just well, possible tiles. I mean, you just have a choice of a row, column, and a symbol, and then a corresponding box for the row and column. And this is basically just the 0, 1 inclusion matrix of edges versus tiles. So we have in a given entry a 0 if that edge is not present in the tile, and a 1 if it is. So now this is the matrix, I guess, that is important for us. But we're going to do something we're going to do something to this matrix that's possibly helpful. We're going to take WW transpose and make this normal system mx equals the all ones vector instead. And you can kind of think about this as saying, very roughly, we're going to solve our system wx equals all ones by just choosing weights on the edges that we have in such a way that all choices that use that edge are going to kind of be spread out and equal. That's kind of what this means in a way. I'm being a bit vague on purpose because I don't have a great way to say it, but yeah, we sort of want to decompose into tiles in a way that spreads out a whole bunch of tiles that share an edge, all giving them the same weight in the decomposition. Okay, so that's something that's legitimate to do in the fractional sense, but it wouldn't really work if you're trying to actually solve this thing on pencil and paper in your magazine. Okay, so now this matrix M, it's now 4n squared by 4n squared, and its rows and columns are indexed by 4 types of edges: row, column, row symbol, column symbol, and box symbol, just like we had before. Okay, now it turns out the entries of M, the EF entry for 2 edges E and F, it will tell us how many tiles contain those 2 edges. So we have N if the 2 edges are equal, that's on the diagonal. And we may have H or W common tiles if there's a common a column, for example, meeting a box, or a row meeting a box. So when bundles intersect, I guess the corresponding box, you could get something interesting here, but otherwise you get a 1 or a 0, just basically depending on whether your 2 edges line up and allow for a tile. So this is what this matrix M looks like, just as a picture. This is in the case 6x6 Sudoku. So it's sort of got this neat little quilt looking structure of we've got N on the diagonal. I tried to use different colors, but it may be hard to resolve them for you. But yeah, and then we've got these sort of, they look like kind of tensor products, I guess, that occur in various other places. All right, so now there are some different relations that are present between edges, which are these row column pairs. Sorry, row column is a type of edge, but of course we got row symbol, column symbol, and symbol box. So rows could be equal or unequal in the same bundle, or they could be in totally different bundles. The same thing with columns. Boxes have a few different ways they could interact. They could be the same box, 2 boxes. They could be the same. They could be adjacent row-wise, sort of, or column-wise, or neither. And symbols could be equal or unequal. And this leads to a whole pile of relations when you look at edges, which are pairs of these things, 69 relations. So it's kind of, there's this large coherent configuration, it turns out. Now, I won't go through the definition of coherent configuration. It's probably familiar to a few people here. But basically, our matrix M from here, it happens to live in a nice algebra of matrices of dimension 69. Well, you might not call that nice. That's a bit big and nasty, but you can do calculations on this. And so we did the following. Oh, sorry, here's a table of relations just to sort of see what it looks like. So, you know, there are 9 different ways that a pair of row column edges can interact. We could have equal rows, or we could have the rows equal in the same bundle, but unequal, and then in different bundles. And likewise, there's these 9 possibilities, and you get a whole bunch of other possibilities when you consider symbols and boxes. So Some minor simplifications of this may be possible, but really it's inevitable there's going to be a lot of different relations. It's a bit nasty. But what we were able to do, though, I thought this was maybe one of the key insights here. We argued with kind of this neat indirect, or we used this indirect procedure to find all of the structure constants for this. It would in principle be possible to compute a given one by hand. It's not hard. But the structure constants here, basically you're given two edges that are related in a certain way, and you want to find out how many third edges relate in prescribed ways to those. And so what we did was we argued that, okay, whatever this number is, okay, it's first of all, it's pretty clear that it's constant by the symmetries that are involved. But whatever the number is, it's going to be at most quadratic in each of H and W. And then, so we just need to find do a few cases of small Sudoku structure constants. Just need to do a few small cases and then interpolate to find symbolic expressions for the structure constants. So let's just say here we've got rows, columns, symbols, and boxes as before as our four partite sets. If we want to choose a row to relate to these two edges in a certain way, well, we basically have some finite reasonable set of possibilities, right? In this case, I either have to pick the same row as this one, or I pick a different row in the same bundle of where there are H-1 other rows, or I pick a row in a totally different bundle where there's N-H possibilities. So I would multiply some number of choices for my rows by, for example, some number of choices for my boxes. And that would depend on whether I want that box to relate to the given choices in certain ways. So I would pick something in the product of these two sets for a choice of the number of boxes. So we argued that these are, you can kind of see here, if you pick two of these and multiply them together, you get something quadratic. Now, there's lots of different possibilities, but you know, we basically stored them on the computer after some interpolation. And now that gets us to maybe this next part where we explored the eigenvalues and eigenvectors. Now I'll rush through this kind of quick here, but this may be kind of interesting because this is maybe the real algebraic graph theory, I guess. So our matrix M from before, it actually, even though it's a bit nasty looking, it actually has really nice eigenvalues and eigenvectors. So you can have a basis of eigenvectors that are ±1, 0 valued. And the eigenvalues are just simply these multiples of n, 0n, n, 2n, 3n, 4n. We showed our eigenvectors in the paper, and I'll do it here, just run through them just to get a look at them with these, this sort of 4n squared kind of, here n is equal to 6, just for illustration. So these four squares, the top left one is rows versus columns. So row column edges are depicted here. Row symbols are over here on the upper right, and then column symbols lower left, symbols boxes lower right. Now, for instance, here is a kernel vector that's eigenvalue 0. Okay, so what this means is we're going to assign, we're going to pick a row, sorry. So say row 1. And we're going to have +1 on all the row column edges and -1 on all the row symbol edges with that row. Okay, so anything that uses row 1 is either plus or minus 1, depending on whether it's a column type or a symbol type edge. All right, now this is the way to think about it, right, is that if you can go through this for each of these in turn, but we won't do it because we don't have time. But if you pick a particular entry, maybe it's row 1, column 2. So this one here, there are exactly n tiles that extend it. Okay, and what we do is we basically say, okay, what is the total value of all, like, okay, I have to, so here I have to pick a symbol to complete it, right? But no matter which symbol I pick, I will cancel out the +1 there because I have a -1 on that symbol, right? So we end up getting 0. And if you've got 0 anyway, like for one of these entries, then the extension to tiles will just will contribute nothing as well, and so you'll get a vector in the kernel by doing something like this. Now you can do something similar where you transpose that, so you exchange the roles of rows and columns. But there are other types of kernel vectors too. Just to point to this one, for instance, here we've chosen the top left box of the Sudoku. So that's this little 2x3 box. And then we've assigned -1 to all the symbols that occur with that box. So now if we extend, for example, row 1, column 2 here, if we extend to a tile, well, we have to pick a symbol, but that symbol is going to be in that box, and it's got a -1 sign, and that will cancel the +1 there when we take the matrix product. So when we take the product with this kind of vector, these are just sort of convenient ways to store the vectors since they happen to have nice +-1 zero valued entries. Okay, so here's some other kernel vectors, and then I'll just give you a look at some other eigenvectors for the non-zero eigenvalues. Here's a neat type of eigenvector for eigenvalue n. So we basically take a rectangle of 4 positions where we've straddled at most 1 box boundary. So that is to say, we want to have either the rows or the columns living in the same bundle. Okay, so if you pick a particular entry here, say the top left corner, there are n symbols that extend it. But interestingly, that symbol is going to occur well, because we've picked at least canceling pair in every box. Then say symbol 4 is going to occur in box 1 with a weight of +1 and -1, and then we're going to get well, you can see that it turns out in the matrix product. I have to hurry here, but you end up getting you get cancellation on entries that aren't shown, and on the 4 positions that are shown, you get a total of n times. So for every symbol that extends this one here, you're going to get a count of +1. So n times, that'll give us an eigenvalue of n. All right, so here's various other eigenvalues and eigenvectors. I'll just race through them. When the eigenvalue here, the eigenvalue is 2n, you start to see some more. This is sort of like choose a pair of rows in the same bundle, assign all the first row positives and the second row negatives, and so on, like this. Okay, here's some more eigenvalue 2n eigenvectors, I guess, shown. We have type A, B, and C here, I guess. There's sometimes some minor variations. Now there's an eigenvalue 3n, which I guess here looks like what's happened is 2 symbols have been assigned. Basically, everything involving symbol 1 is positive. Everything involving symbol 2 is negative. And if you think about it that way, if you extend a choice of, say, row symbol, there are n columns for it. And you're going to end up getting a total of 3 weight in each tile that extends it, and so you'll get 3n for the eigenvalue. Okay, so finally, there's this nice eigenvector, which is super simple to imagine. This is just everything's equal to 1, and the row sum of our matrix M happens to be 4n because there are 4 edges in a tile and and n ways to extend a given edge to a tile. All right, so now this is where the real substance happens. I'm sorry, I got to cram it in at the end here, but basically we can write our symmetric matrix M using spectral decomposition. We can write it as eigenvalues, a sum of eigenvalues times projectors onto these eigenspaces. We don't need to worry about the kernel, I guess, but yeah, so we get some kind of a nice decomposition like this. So we made these pretty pictures that sort of depict the projectors, so we get this spectral decomposition, and maybe you'll believe me that in general, with those symbolic structure constants we had before, we stored many symbolic structure constants from our interpolation procedure before. We can actually find coefficients for these in general, right? For these projectors, E1, E2, E3, E4. Okay, so now with that, we can get a generalized inverse for our matrix M. Now, M had kernel vectors, right? Remember, so M was not invertible. But if we just take a shift by some multiple of K, the projection onto the kernel of M, then we can invert this shift, right? And you can pick a good value to shift by so that you get a fairly small infinity norm for this generalized inverse. Now, infinity norm is the sum of the absolute values, the maximum sum of the absolute values along any row, and so maybe you'll believe me, it takes some computation, but you can get an upper bound that is basically big O of n to the -1 here, and the constant happens to be 15/4 for this choice of x that I picked here. Okay, so now the perturbation part of this. Basically, I'm going to go through this pretty quickly, but here's the idea: if somebody's given me a very empty, very sparse Sudoku, then I can reasonably assume that that the linear system for it will be fairly close to the linear system for the empty Sudoku, which we just analyzed completely. This kind of tells us how to solve the empty Sudoku, but that's a bit silly because empty Sudoku, I mean, even a child could write down a solution, so it's not really very interesting. But if our Sudoku is sparse, right, then we can, in the sense that maybe we can bound the infinity norm between what we're given and the empty one. That is, if no row column symbol or box is used very often, and we also have this symbol bundle condition as well, then we can get a bound on well, okay, let's just take this out of the box result here. If you have an invertible square matrix, so you get this invertible matrix, so A, and then you have a perturbation by subtracting delta A, then as long as A inverse delta A is less than or equal to 1/2, then you have a non-negative solution to the perturbed matrix times X equals the original matrix times all ones. In other words, if you have an all ones solution and you perturb it by something that's small in this sense, then you're going to still get a non-negative solution. And we want a non-negative solution to get our fractional Sudoku. So the idea of the proof, by the way, here is just to use a series expansion of the inverse of the perturbation. So that's pretty standard. But what we're going to do is take an epsilon dense partial Sudoku. Okay, and it's going to be the usual H by W boxes. All right, and we'll define M sub S similarly to M, except that now instead of it just having these what were they, maybe 5 different values, now we have the number of tiles containing a given pair of edges being the entropy. And that could vary, right? But it's going to be some slightly smaller matrix and slightly restricted matrix because we may have lost some edges, but it's going to be kind of close to M. And if it's close enough, then we can invoke the previous theorem or lemma, I guess, on perturbation. Now, a little bit of a white lie here. Our M sub S differs from M by something that's basically, it's the important thing here is it's O of n where we have dependence on epsilon as well. So 12 epsilon n. So basically, there's 4 edges in a tile and 3 other edges from a given one, and 4 times 3 gives you the 12. And yeah, I mean, maybe you believe that now the white lie is that we actually need to border the M sub S with something so that it's the same size, because you cannot subtract matrices of different shapes, right? We learned that in first course in matrix algebra. But with that aside, right, we can put a little border around our matrix M sub S to basically cover those edges that got filled in by the puzzle creator. All right, so now here's the main result finally. Suppose epsilon is small, and here small can be up to 1 over 101. Okay, so for sufficiently large H and W, every epsilon dense partial Sudoku with those H by W boxes has a fractional completion. That is, we have an assignment of positive rational frequencies or values to the symbols in unfilled cells so that Sudoku conditions hold. And here's an example of that. So the puzzle creator here, oh, by the way, I actually used the algorithm that that produced the perturbation stuff to get this to make this image. So somebody's given us 3 filled entries ahead of time: a red, a purple, and a green disc here. And then here's a fractional completion. So in the top row, there's a total of 1 red. Okay. In, say, the 4th column, there's a total of 1 blue. Okay. And so on. And in this, I don't know, this lower, say this lower left box, each symbol occurs, each color occurs with a total of one pi worth of that color. All right, and basically you get the proof idea. We're nearly done here. The proof idea is basically just to invoke that perturbation result. It's pretty naive. Just use the out-of-the-box perturbation result together with the inverse of the nice structured matrix that lived in the algebra, which had a upper bound on its infinity norm of about 15 over 4n. We can use submultiplicativity here to split up this. You know, you can no doubt do a bit better. And in fact, it's hard to find in practice a partial Sudoku that doesn't work with this method, but the bounds only guarantee it for about 101 over 101. Okay, so just to wrap up, I omitted some details on bordering. I'm sorry about that, but you can look in the paper for more. I'll give you a link to the paper in a sec. Interesting. If the boxes are very thin but long or tall, say one of the parameters is fixed and the other parameter grows, H and W, then you can actually drop the bundle condition. And we showed that by basically filling up all occurrences of a filled symbol in a box in one of these bundles. We sort of completely filled the bundle with that symbol, and we still showed that we didn't get too much filled, so that we could still use the perturbation. Oh, you could apply this to some non-rectangular boxes as long as they're approximately rectangular. I should mention that. Same kind of idea can work there. You get a little bit of a worse bound, though, and we weren't actually explicit with the bound, but that's maybe some future research could look into that. Yeah, I mean, the big question is, can you actually turn fractional into exact completion? I don't know. We don't know how to do that. The methods of Barber, Kuhn, Low, Ossis, and Taylor that do that for Latin squares does not seem to be available for Sudoku because it's a little bit more annoying a structure. But I suspect there could be something possible there. That's it. Thank you very much for your attention.
Thank you. Are there any questions for Peter?
The paper is the top link there. You can probably just better to Google it, I guess. But yeah, if you want to see some more details.
I have a self question, if you can hear me.
Yeah, I can hear you.
You had the pictures which you described as being quilt-like.
Yeah.
How did you get those? Generate those?
Oh, so I should say a lot of the computations were done using Sage, which is overlay on Python. You probably all heard of Sage, but I basically just I made a little function that turned a matrix into a quilt, I guess, by you know, just taking the union of a whole bunch of squares of different colors chosen according to the entries. Oh, but the colors sort of show a heat map of the value of the entries. White is 0, and I think something more bluish is like greenish and bluish is positive, I think, and red and orange are kind of negative. I think I just used some kind of a scheme like that.
They're very pretty.
Yeah. Oh, thank you. Yeah. I kind of like those. Yeah. Well, I don't like the last one. Yeah.
Hard to avoid it, though.
But ironically, that last one is why the whole thing works, right? Yeah. Yeah. Any other questions, comments?
maybe the wrong question in a theory sort of context, but where do these fractional Sudokus come up in practice? Are there like any applications for these in mathematics or in operations research?
Ah, that's a really good question. I don't know that Sudoku would probably have any applications that are, I mean, maybe more natural is just to start with fractional Latin squares, which, as I mentioned, this sort of actually followed the same tour as we did for Latin squares, which was much nicer in the algebraic sense. Like the algebra of matrices was actually a Bose-Messner algebra. It only had dimension 5, so it was a lot nicer. And it's in fact been studied before. I guess that fractional, here's one thing to say: you can clear denominators if the denominators are reasonable, and you can get some kind of a balanced plan for maybe testing or arrays or something like that. It's going to give you something that has many of the same qualities as a Latin square. I should also mention that fractional weights on things can actually be used by statisticians, I think, in the design of experiments, in the sense that you can assign probabilities to the events that according to the fraction that the thing is present. So maybe you test IJK together in a triple if with probability equal to the fraction that it occurs. Actually, to be quite honest, the way I got into fractional decompositions was through that, which is interesting because I'm not a statistician and I'm not really that interested in those applications. But a colleague of mine thought it was connected enough to design theory type things that it may be interesting. And then, yeah, that was many years ago, back when I was just out of grad school. So I think there are some nice statistical applications, but I'm sorry, I don't know more. I think there is just a nice aesthetic feature to having this balance occurring, and either by probabilities or by clearing denominators, you can make some kind of a testing scheme, I guess, similar to what you would use Latin squares for.
And then the math itself is interesting enough.
I guess it's kind of fun. Yeah, I like seeing new applications of coherent configurations and things like that. Yeah, that's good.
I was also going to ask a question.
Yeah, Josh, go ahead.
I was going to say those equations earlier on looked a little like something from design theory, like the W times some integer vector is a multiple of the all one vector.
Totally, yeah.
I was going to ask if you ever looked at anything like the like diagonal forms of the W. That's how you maybe go about trying to find integer solutions.
That's great. So in I mean, I actually I prefer to work with the simpler W that come from either Latin squares or just the dense graph case of triangle decompositions. Of course, in the case where W, you probably know this given that you asked the question, but in the case where W actually underlies a design, then yeah, the diagonal forms have been investigated by Rick Wilson and others, even into back into the 90s and stuff. So a lot is known about that. With Sudoku, though, no, I haven't explored the diagonal forms. That's maybe the next student can look at that. That's a good question. In fact, I don't believe the diagonal form for the Latin square case has been studied, although I don't know all the literature in my head right now. But I think that case may be open. But we have a start on the diagonal form, I guess, from some of the spectral analysis that has been done before. So that's a first start. But yeah, that's a good question.
Yeah, thanks.
Yeah, I don't know is the short answer. Yeah.